In this video, we'll introduce the helium atom. We'll talk about the energy of the helium atom. Then we'll talk about spectroscopic notation. And finally, we'll talk about the generalized helium states. So a multi-electron atom in general will have an atomic number Z. And it can be described as a heavy nucleus, stationary nucleus, because we made the assumption that the nucleus doesn't move, of charge Z times E, where E is the charge on the electron. It's positive. Surrounded by Z electrons, each of charge minus E. So the Hamiltonian for this system is going to be as follows. It's a sum from J equals 1 to Z of minus h bar squared over 2m Laplacian for coordinate J, minus 1 over 4 pi epsilon naught Z times E squared over R sub J, plus 1/2 times 1 over 4 pi epsilon naught sum over J not equal to K all the way to Z of E squared divided by the absolute value of R sub J minus R sub K. So this term is kinetic energy for the individual electron. This is the Coulomb attraction to the nucleus for the individual electron. You'll notice there's a Z here because that's the charge on the nucleus. And this is the position or the distance of that specific electron, the jth electron, from the nucleus. And then you have this sum of the repulsion between the electrons. Each electron repels the other. So this is going to be a repulsive force. That's why it's positive. It's a Coulombic type force or potential because 1 over 4 pi epsilon naught, it goes like the distance between the two electrons to the minus 1 power times the charge on the electrons squared, E times E. And then you have to sum it over all the electrons in the multi-electron atom all the way up to Z, but you want to exclude the self-repulsion because it doesn't exist. And then you divide it by 2 because when you do this, you're double counting. You will count the force between the J and the mth, or the M and the nth one, one way when you go from M to N, and the other, and you'll count it again when you go from N to M. And so you want to divide by 2 to get rid of that. Now, this is a Hamiltonian that can't be solved in closed form. And we'll spend some time later on seeing how we can solve these with perturbation theory. But we can look at the qualitative features of the system by just ignoring the electron repulsion term. So we're just going to throw this term away because this is the term that is a little bit more difficult to deal with because that couples two electrons. So if we ignore the electron repulsion, we still must properly anti-symmetrize the wave functions with respect to the exchange of any two electrons in a system. So if we have Z electrons, then we have, if we apply the exchange operator to this wave function, which goes like R1, R2, all the way to R sub Z, and times the spin wave function, because we can't ignore spin, S1, S2, all the way to S sub Z. When we apply that and exchange R1 and R2 and S1 and S2, you get psi of R2, R1 all the way to RZ, chi of S2, S1, all the way to S sub Z. And that must equal to minus the original wave function, psi of R1, R2, R sub Z, chi of S1, S2, all the way to S sub Z. And this should hold for the exchange of any two electrons all the way up to this, from 1 to the zth electron. Well, let's simplify this by looking at Z equals 2. So it's the helium atom. And now we're going to ignore the electron-electron repulsion, and we're going to have a Hamiltonian that looks like this. It only has two terms now, and the two terms are separable. That is, H is approximately equal to minus h bar squared over 2m del sub 1 squared minus 1 over 4 pi epsilon naught 2 e squared over r1 2 being Z, the charge on the nucleus, plus minus h bar squared over 2m del sub 2 squared, minus 1 over 4 pi epsilon naught, 2e squared over r2. Now, because we've removed that electron-electron repulsion, the electrons are non-interacting, and the equation, as I said, is separable. So we can get solutions to these independently, and each of them will look sort of like a hydrogen-like function. And we'll then, because they're separable, we will have a product state. Psi of R1, R2 is psi NLM of R1 times sine N prime L prime M prime of R2. The energy, total energy, is going to be 4 times E sub n plus E sub n prime. And there's a 4 there because of this 2, that is Z is equal to 2. That's important because that makes the energy quite a bit higher because that potential well is deeper. The magnitude is much higher. And this is going to be equal to 4 E sub 0, 1 over n squared plus 1 over n prime squared. So, we can now write the ground state. The ground state, psi 0, is the hydrogen-like wave function, psi 100 of R1, times the hydrogen-like wave function, psi 100 of R2. And then, because this is a symmetric function, right? The spatial part is symmetric. The spin part must be anti-symmetric, the way we've written this down. So we get chi 0, 0 is the anti-symmetric spin singlet. And we write that as chi 0, 0 sub 0, 0 of S1, S2. And we can rewrite that just by expanding. These two functions are the same. You get R1 plus R2 in the exponential, so it's 8 over 4 pi over pi a cubed e to the minus 2 R1 plus R2 over a times 1 over the square root of 2 times spin up for particle 1, spin down for particle 2, minus spin down for particle 1, spin up for particle 2. So this makes the whole wave function anti-symmetric. And that's important. If you have a symmetric spatial function and you want an anti-symmetric function overall, you have to make an anti-symmetric spin function. Conversely, if you have an anti-symmetric spatial function, you can use a symmetric spin function and get the total function, wave function, to be anti-symmetric. The energy then, E sub 0 for this state, is 8 times minus 13.6 electron volts, which is minus 109 electron volts. Unfortunately, that's a very bad estimate because the actual value measured to 5 significant digits is minus 78.975 electron volts. So we're off by a significant amount here. Right? We're off by over 30 eV. Now, all that missing energy is due to the electron-electron interaction, because that's what we left out. So if we ignored the electron-electron interaction, we obtained that the energy of the helium atom is about minus 109 eV, while the measured value is really minus 78.975 electron volts. How can we understand this large discrepancy, besides knowing that it's from the electron-electron repulsion? Well, we can consider the energy of a helium plus ion, which has a positive charge nucleus of 2e and only 1 electron. We know what that is. That's going to be 4 times, the energy of that is going to be 4 times minus 13.6 eV. And that's minus 54.4 eV. If we now look at what the second electron sort of sees, it does not see the full 2e of the nuclear charge. And the reason is that that first electron is screening some of that charge because it's already in an orbital that's symmetric about the nucleus, and it has some possibility of being very close to the nucleus. So if your second electron is outside the first electron, then it won't see a full charge. It'll see something less than a full charge. On average, it'll see something that's in between 1 and 2e. Well, if we take the energy difference between the helium plus ion and the experimental helium atom energy, we get, it's about 79, it's about 24.6 electron volts. If we consider that 24.6 as an effective z squared, right, this is just z squared and z is 2, times minus 13.6 electron volts, we can find that z effective squared is 1.81 and z effective is 1.35. So on average, the second electron sees about 1.35 e of charge from the nucleus because of the screening of the first electron. So the screening effect gets even more pronounced in heavier atoms, and it's important in determining how the periodic table is generated. As you get more and more electrons, systematically the lower values of angular momentum are filled first, and they provide a more effective screening of the nuclear charge. And then we can build up the entire periodic table. Now, a note about spectroscopic notation. The spectroscopic notation contains all information about the angular momentum of a state in a compact notation. And it's very useful to know how it is because you'll see it a lot in spectroscopic studies. What does it look like? Well, it has this form. You have a superscript 2s plus 1, then you have a large L and a subscript J. So the term symbol, which is L, is a letter that indicates the value of the total orbital angular momentum. And you do that by summing over all the electrons in the highest occupied state. So this is the total angular momentum added, as we've done before when we add vectors. We add these vectors. And that's the value of all of them in the highest occupied state. The superscript is the total spin multiplicity of the state, and it depends on the value of the total spin for angular momentum. Spin angular momentum S for all the electrons in the highest occupied state. So however those total spins add up for those outermost electrons, then you put 2s plus 1 up here. And finally, the subscript J identifies the value of the total angular momentum J, where J is going to be L plus S, and we add those just like angular momenta, because they're both, this is intrinsic and this is orbital, and it's according to what's called the LS coupling. That's one of the coupling means that you can couple spins and angular momenta to get a total angular momentum. With this in mind, we can now look at the generalized helium states. So we have excited states of helium consisting of one electron in the hydrogenic ground state and the other electron in a higher level. So one electron's in the 1,0,0 state and the other electron is in a higher level, NLM. Each excited spatial state can be symmetric or antisymmetric, and so it can have either singlet or triplet spin states. Now for singlet spin states, this is called perihelium, S is equal to 0. And orthohelium is the triplet state where S is equal to 1. Remember the total spins for the two electrons, each of them has a spin 1/2. So you can get spin 0 or spin 1 when you add them together. So that's what the total spin of the two electrons in the helium atom would be. So the ground state is by definition perihelium. And that is because if you have 1,0,0, 1,0,0, that's a symmetric wave function spatially. You must have an antisymmetric spin state, and that's the S equals 0 or perihelium. So that's sitting down here at a low energy. Now notice this is the energy 24.6, minus 24.6, which is the difference between the energy when you put of the helium plus ion and the helium atom. So we're not doing the total energy, which is minus 78, but we're just looking at the additional energy that you have when you put that second electron in. When you put the second electron in the ground state, in the 1s state also, you get an additional minus 24.6 eV. Now, let's look at what these are. All the perihelium states over here are spin singlets. All the orthohelium states over here are spin triplets. So, the perihelium states are symmetric spatially, and the orthohelium, which are symmetric spin-wise, must be antisymmetric spatially. Perihelium states typically have a higher energy than the corresponding orthohelium states, and that's because these are due to the exchange forces, which force the second electron further away from the nucleus to stay away from the first electron, which is in the 1s state. So that's why this second electron going in the 2s state in a perihelium, that is a spatially symmetric state, is higher than the 2s state here, where it's going into an antisymmetric state. So one electron is always in the 1s state. So the total L, which is down here, which is described here in the term symbols, is equal to 0 plus whatever L of the second electron is. So let's imagine we have the second electron in the 2s state. That means that its L is also 0, and therefore, when you add 0 and 0, you can only get 0, but that means that the term symbol is an S. Similarly, for the 3s and the 4s states, they're all equal to a term symbol of S. They're in a perihelium state, so 2s plus 1 is equal to 1, and that's why you show this point here, which is 1s. Now in this term symbol, we've ignored the J, the total J. But the total J is L plus S. S being 0, L being 1 is going to be 0 here. So we're going to ignore this. We'll work on the total J later on when we do multi-electron atoms further on. If you have the second electron in a 3D state, then L is equal to 2 for that second electron. And that means when you add those states, capital L is also equal to 2, and that means the term symbol is D. And similarly over here, the same thing, but now the superscript in the front is 3 because S is equal to 1, so 2s plus 1 is equal to 3. For perihelium, J is just equal to L because S is equal to 0. So this would be a 0. This would be 0, 1, 2, 3. For orthohelium, since S is equal to 1, J is going to be L plus 1. So in this case, this will be 1, this will be 2, this will be 3, this will be 4. So 0, 1, 2, 3, 1, 2, 3, 4 for total J. They're sort of trivial in this case. So for orthohelium, we can imagine for the 1s, 2s pair, you have L is equal to 0 in orthohelium where S is equal to 1. L is equal to 0 because both L's are 0. S is equal to 1 because it's orthohelium, so J is equal to 1. For the 1s 3D in orthohelium, we'll have L is equal to 2, S is equal to 1, and J is equal to 3, 2, or 1. So we have a bunch of different possibilities, because when you add L and S, remember you get all the possibilities between the sum and the absolute value of the difference of those J's. So in this case, there's only one state. In this case, we don't know which one will be the ground state, which one will be the lowest energy state of the J equals 3, 2, and 1, because there are three possibilities.